This is a short tutorial about chemical machine programming. In this tutorial, I will illustrate how to implement a game, a very simple game, using the chemical machine. And I will show Scala code using the library Chemist. The game will be to guess a number. This is a familiar game where you choose a number, say, between 1 and 100, and the player can ask questions. Is this number greater than 50, or is it greater than 75, and so on. And in this way, eventually guess what the number is. However, we will implement this game with a twist, which is that, first of all, answers come after a delay. They don't come immediately to the player. So the player asks, is the number x greater than 50, but the machine answers after an unpredictable delay. Let's say this is because the answer requires some kind of computation, and the time necessary for this computation is unpredictable. While the player is waiting for the answer, the player can ask another question. So the player should be able to ask any number of questions while waiting for answers, and answers will arrive each after an unpredictable delay, so the answers will arrive perhaps out of order. So all of this must be asynchronous. The player should be able to ask questions at any time. However, it would be inconvenient if the answers are printed while the player is typing the question. So we introduce the constraint that the machine may not print any answers during the time that the player takes to type the question. Now the question consists of typing in an integer, and that's the constraint. So while the player is busy typing, the machine may not print any of its answers, even if they are ready. Once the player finished typing, the answers might be printed. So in other words, the console, the terminal window, is either at the player's disposal or at the machine's disposal, but not both. So this models contention on a resource. The resource is the console, and the contention is that the player wants to use the console to type the question, and also the machine wants to use it to print answers. So to make the specification of the program quite precise, let's imagine that we are using just a standard terminal input, and the player indicates the beginning of a question by pressing enter. After that, the console is at the player's disposal, and the player will type an integer value, and then finishes typing that question by pressing enter again. So types an integer value and presses enter. And after the player pressed enter, the machine is free to print answers that are available now, line by line, until the player again indicates that a new question should be asked by again pressing enter. So once the player presses enter again, the console should be at the player's disposal, and the machine should not print any answers, even if they're available, until the console is idle again. So that's the specification of this game, and I will now show how I can implement this game by reasoning about this asynchronous and concurrent computation. So let's first get out of the way the various helper functions that implement the specific computations and messages in the game. So the first function would be to read the player's question. So the function will first print a prompt, such as your question is x greater than, and we're printing it without the new line. So this is not a println, this is a print. And so then the user can type the number here and press enter. This will be captured by this read line. And if the result is an integer, then we return that integer. And we also print the message here, please wait for the answer, with a new line. So that's when there's no error. When there's an error, we print an error message and call the same function again, so that the user can again type another integer maybe. So that's one function. Another function is to compute the answer message. So if x is the secret number and guess is the player's question, then if they're equal, we return the message that everything is correct. Otherwise, we return the message that the number x, which is the unknown secret number, is or is not greater than guess. So that would be the response of the machine. Note that we also show what the guess was, because the player can ask many questions asynchronously, and the answers come perhaps out of order, and so each answer should say what the question was. And so the answers will be messages such as, the number x is not greater than 50, or the number x is greater than 25, or something like this. And finally, the auxiliary function to delay. So this will simulate the computation that is necessary to get the result, the answer. And we're just going to delay between 10 and 20 seconds randomly. All right, so to initialize the game, so this will be just one run of the game, we'll not be playing again and again, just for simplicity. So we initialize the game by choosing a random number between 1 and 100 and printing the initial message that indicates the start of the game, telling the user to press enter to begin. So let me actually run this code to see how it works. Below, I have already implemented this game, so I will just play now once to see what is it that we want to achieve in the implementation. And then I will reason about the necessary implementation and derive the chemical machine code from that reasoning. And in this way, show how the chemical machine allows me to reason about my code. All right, so I'm pressing enter. Is x greater than 50? I ask. I again press enter. Is x greater than 25? I ask. I again press enter. 75, I ask. I got an answer that it's not greater than 50. Let me do 35. Let me do 15. I just let it wait a little. But I could keep asking questions. Okay, it's greater than 35 and less than 50. So let me get 40. Let me get 45. let me get 37, and I can enter more questions. Okay, it's between actually 35 and 40. That is good. Let me do 36. And oh, it's greater than 37. So let me do 38 and 39. So each time I pressed enter to get a new question, but until I pressed enter, the machine could print. So now the machine can print its answers. I'm just going to wait until. All right. So the actual number was 39. So I got it, and the process is finished. So that is the interaction we want. How do we implement it? So clearly the console is in one of two possible states. Either I'm in the process of entering a number, or I finished a number or never started, so the console is free. I'm not owning it. These are the two states. Now, so this state needs to be modeled, and so we model it by having a molecule, and clearly there's a contention between the player and the machine on the console. So let us model this contention by a molecule. So this molecule, let's call it can show. If this molecule is present, and it should be always present, it's a contention marker or a contention token, then either one reaction or another reaction will consume this molecule. And in this way, only one of these two reactions will run. So this is a mutual exclusive contention token, which we just model by making it a molecule, say with can show and with unit value. And clearly the two reactions that are necessary that will consume can show. One reaction is going to print the machine's answer, and the other reaction will read the player's question. So the first idea, therefore, that we arrive at is that we need a contention token, and two reactions will be running exclusively, either one or the other, because either the reader is typing the player is typing a new question, or the machine is computing or is printing a new answer. So let us try to see how these reactions would look. So these reactions should look something like this. Consuming can show, and then I read the guess and do something, or I consume can show and I print the answer. Now, so this is kind of what is necessary. Now, clearly we cannot print this answer because can show doesn't have any information. Can show is a unit typed molecule. It's just a contention token that makes it impossible to run these two reactions in parallel. And we will have to make sure that we have always a single copy of the can show molecule emitted initially. So then only one of these two reactions can run. And also we should make sure that we emit this can show back into the reaction site when each of these reactions is done. So in this way we do a mutually exclusive contention resolution. Now, obviously we need another molecule that will carry the answer message. So this reaction cannot work. It cannot print an answer message unless it gets that on an input molecule. So we need another input molecule for this reaction. So let's call it answer. It will carry a string value. And now we can run a reaction like this, where we print a message that is consumed from the answer molecule. Now, who will emit the answer molecule, though? So now this reaction is fine, but somebody needs to emit the answer molecule. Well, clearly, the answer molecule can be emitted only by a reaction that computes the answer, that takes the question and computes the answer. Now, this reaction would have to be of the form like this, consuming a question molecule of some kind. Well, it needs to consume some molecule. No reaction can start without consuming a molecule. So let's say this molecule is called question. And clearly, this molecule should carry the user's question data on it. Then we can make a delay and send the answer, compute the answer and send it. Now the delay is just imitating a computation in this little tutorial. So we define a question molecule with integer type. But what reaction will emit that question molecule? Well, clearly the reaction that reads the player's input that we already started to write. So therefore, this reaction should look something like this, where we evaluate the read-guess function to read the user's input. Then we emit the question molecule with that value that the user gave, and then we emit can_show as we have to which is just the contention token, as I call it. All right, let's continue reasoning. So far, we have implemented the functionality of answering the questions and of entering users' information, the player's guess. But we have not implemented yet the requirement that the player should press enter in order to start entering a new question, because we need this functionality. After the player has entered one question, the console is idle. Another enter press is required in order to start entering a new question. So obviously we need a reaction for this, and this reaction should have code something like that. So it should consume some molecules, then call the read line in order to consume the enter, require the player to press enter, and then maybe emit something else. Now, when would that reaction start? So we don't know what molecules it consumes. In order to figure that out, we need to understand when we want this reaction to start. Well, only when the player has finished asking the previous question, and the console is idle. So, therefore, the previous reaction that finished reading the player's question should emit some molecule that goes here as input. Now that molecule cannot be question, it cannot be can_show, because those are already busy doing other things, so this needs to be a new molecule. Let's call it idle. And we mean that if this molecule is present, the console is idle. The player has finished asking the previous question and is not using the console. So this molecule should be emitted by the reaction, this one that reads the question. So we have to add this over there. And at the same time, this reaction should be unable to start, so we should emit it here, maybe. But this is not enough, because this reaction should be unable to start while the console is idle. If the idle molecule is present, it means that the console is idle. It means that this reaction cannot start. The only way to prevent this reaction from starting is to withhold some input molecules from it. But this input molecule cannot be can-show because that molecule is always going to be there. It's a contention token. So we need a second input molecule in this reaction to enable or disable this reaction. So let's call this molecule can-ask. So this molecule will be present if the user can ask a question. So let's define therefore the idle molecule, the can-ask molecule, and we added the idle molecule at the end of this reaction. And we need to do this. So can-ask needs to be another input molecule in this reaction. Idle needs to be emitted at the end of this reaction. So we emit 3 molecules, we consume 2. And the idle reaction is like this. It reads the line and then it emits this can-ask, which enables asking the user, asking the machine another question. So in this way, idle is consumed, can-ask is emitted, or can-ask is consumed, idle is emitted. So either can-ask or idle are present at the reaction site, but not both. So in this way, we model the console state. Its console is either idle or the user has requested to ask another question, and then the console is no more idle, no longer idle. So now that is basically the entire functionality, except we want to implement the end of game. So if the guess was correct, we want to exit the entire application, as we have seen in the demonstration. So we want to finish our process, not just keep waiting. How do we do that? We introduce 2 more molecules. One will be blocking, which will wait for game over in a blocking manner. And the other molecule will be non-blocking. It will just indicate the game over. And then we have this usual pattern where game over reacts with wait for game over and sends a reply to it. And the game over will be emitted instead of the answer molecule when the guess is correct. So this is now the entire complete code of this game. I have reformatted a little bit, and this reaction that computed the answer is now doing a little more work. It computes the answer message, and if the guess is correct, it gives a game over molecule with the answer message. Otherwise, it gets the answer. It emits the answer molecule with the answer message. And the game over molecule reacts with the wait for game over and prints the final message, which is going to be correct. The number is such and such. So that's the entire code. And initially, we need to make sure that we prepare the initial state correctly. The console is initially idle. The user needs to press enter in order to start entering a question. And that's the initial message that we printed back at the beginning. Press enter to begin. So that means we need to prepare the console in the idle state initially, so we emit the idle molecule initially. We emit the contention token initially, which must be emitted. It's essentially a static molecule, which I can make static explicitly to reduce possibility of errors and perhaps to optimize the execution. And finally, I emit this blocking molecule, which waits for game over. When this molecule receives a reply, I exit the program. So in this way, I implement this simple game by declaratively modeling what needs to be done and what tokens or molecules or information I need to pass from one process to another. In this program, you notice I'm not saying how many answers are being computed at once. So this delay function is simulating a computation. I'm just doing a thread sleep here, but I'm pretending that I'm computing the answer, that it takes time. If many questions are asked, many question molecules will be emitted, and many copies of this reaction will run concurrently in parallel. The code does not express this directly. The code does not say, make another thread and run it. The code just says, when the question comes, do this. If many questions come, the runtime system will decide how many copies of this reaction can be run in parallel. This depends on the number of cores on your CPU, or other such considerations, and this should not be a concern of the code. So this is one illustration of the automatic parallelism that the chemical machine has, and you have seen during the game that many answers arrive at the same time, or almost at the same time, asynchronously. And this is because these answers have been computed in parallel, and they take different time to compute. And so many copies of the answer molecule could be emitted at once, but only one of them will be printed at once. So this printing is not is thread safe, so to speak, because this reaction has a contention token. And if the user wants to ask another question, then the contention token will be consumed. We will be here in this computation in the read-guess function. While we are in the read-guess function typing our integer, there is no contention token present at the reaction site, and also idle is not present. And so none of these reactions can start. It cannot start printing another answer because the can-show token is not present. And so in this way we resolve resource contention regardless of how many answers arrive at once or very shortly after one after another. All of this is automatic. The code does not have to worry about such things. Our code is declarative and does not worry about the order in which answers arrive. When they arrive, and once we are able to show the answer will be shown. However, it is important to have a single can-show token in the reaction site. So that is actually an important part of modeling. It's a contention token. It must be emitted at the start, but only one of them must be emitted. So this reasoning is part of the chemical machine paradigm. You have to reason about how many copies of a molecule you want to have at the initial time. So this concludes the tutorial, and I would like to just note as a comparison, you can try to implement this game using a different concurrency paradigm. This algorithm expresses parallelism together with a contention on a single copy of a resource. Now, this kind of pattern, where you have many processes that need to share a resource, this is called reader-writer problem, where you can have different processes, many readers, many writers, but they need to resolve their contention. Only one console is available. So either you're reading or you're writing to it, but not at once. So in this simulation, we have a single reader here. Well, we actually have another reader here. So we have two readers, but only one of them can be active at a given time. And we might have many writers, because many answers could arrive almost at the same time. And so we need to resolve this contention before we implement this correctly. Somehow we need to resolve the contention between multiple writers and these two readers. Each of them also can be active only at one time, so there should not be at the same time trying to read this and read this, because that would be incorrect. Not what we want, because this read line is to skip when the user is here or here, please wait for the answer, and then I want to ask another question, I press enter. So there's this empty line here, which is when I pressed enter, and that line is read by this read line, which is the second reader. And then there's a can ask, and I'm here and I can enter my integer. Try to implement this in some other paradigm using akka or using just plain futures with thread pool executor. You will find it not so easy to write code correctly. Here I have written code correctly pretty much the first time through. I had some iterations on how many molecules I need, but these are basically reasoning that's straightforward. I need to prevent some reactions from running. The only way of doing so is to have extra input molecules that aren't yet there. So then every time I needed to do something like that, I had to introduce an extra input molecule. That kind of reasoning, and then I basically got the code correctly. And finally, there was reasoning about what the initial molecules should be. And that was it. A program in the chemical machine is a declaration of possible reactions and a specification of what initial molecules need to be present at the reaction site. And that's the entire program. There's nothing else here. Well, there are all these helper functions that compute messages and so on. I put them in a separate code so that they don't make this code too long. And basically that's it. So I have here maybe 15 lines of code to implement the entire logic of this game with game over, with waiting for game over. I have another maybe 10 lines of code to define all these things that I need, and I'm done. So try to implement this in a different paradigm, and you'll see most likely that the chemical machine code is easier, shorter, and more correct by design. This ends the tutorial.